All right. I'm happy actually, Maria, that you invited me to talk, and I have also quite interesting things to say. I believe this is a very new thing. So whatever the subject of our talk today is has been developed this year, basically. In January, nothing existed. What we produced, what we have today, and one word, um, let me start. Okay, this I just click on the link, but let's go back. This I'm going to reset it and start again. So, like Maria already said,
Ioan, sorry, if you
yes.
want to say some few words about what the UNDP is doing.
I was thinking to start a little bit here because I have some slides where I will stop with that. I wanted to let them know, and I will start by saying that this is also not something really new. Last year I was also here. Of course, probably most of you, at least I hope you are not in the same class, and therefore to me, it's already a little bit of deja vu. But what I want to say here is that today, the geospatial, the webGIS has evolved into something very different compared to 10 years ago. Purely the proliferation of cloud technologies has generated a lot of momentum in the market and has enabled many organizations and many ways how geospatial information can be created, shared, and consumed. So this is purely related to the fact that there's a lot of big cloud, smaller cloud companies. So suddenly we ended up with from a classical web application where we have a web map server with a JavaScript and HTML client. You probably know all UMN map server. We ended up with something really nice like Slicky Maps, powered by Mapbox, powered by vector tiles, new technologies, and a lot of changes. So in essence, today the web GIS has transformed itself into centralized and accessible data, a data mapping services powered by various mainly open source. Let's say I use open source, but there's also commercial ArcGIS is also very powerful with data services, and not the last reactive web components. So you have engines like map engines. MapLibre is a very good example. It's a fork of Mapbox. And these together now, it's very easy actually to build platforms. So this is what GeoHub currently is under its root somewhere in its core. It's just a bunch of components really like open and tied together into one unified concept. But then, of course, nobody builds these things just to have fun. So why do we really need these tools? In essence, is to create insights. This is what we call it in UNDP. Insights are basically for you conclusions that you arrive at by conducting spatial analysis, doing any sort of visualization, exploratory data analysis, spatial statistics, and whatever you can conclude from that is the result of that process is powering insights. And we call it analytics and insights. This is the ultimate goal of GIS, and WebGIS has now been empowered to reach almost the same level as a real desktop these days. Obviously, I'm going to take a small detour here and say that we are all witnessing various things. Climate change, this is an example of a catastrophe that happened in 2023. A whole city was devastated. Now, UNDP as an organization has various attributions and mainly is related to developing and development project. But inside itself, as alone, on top of this development, there's also a group and a whole division dedicated to crisis management. So these type of analytics and geospatial platforms can be very useful if tailored and designed in a way to be useful to these crisis bureau colleagues of mine. So this is absolutely, we're going to see immediately, but currently the focus is on crisis, and the GeoHub I try to develop with my team together and analytics to support the crisis colleagues. We call this Rapida. For example, when you look at this slide here, right, you can see, okay, it happened somewhere. You can see the sea. Well, you know, probably it's on the coast. But if you think about it for a minute, how do you really find where this happened? Quickly, imagine that the goal when we talk about crisis, whether they are handled in UNDP, in WMO, anywhere in the planet, in your government, you know, time is of essence. So you don't have a lot of time. That's what I said, that the GIS has to be tailored. It has to be very timely. You have 1 to 2 hours to provide results. They don't have to be perfect. They have to be, because always perfect is deadly. But you need to provide them with something. We need to provide them with any type of information that it doesn't have to be perfect, but it can help quickly to mitigate. So the timeliness is very important in this. So obviously, you know, this is an example of how I try to say, okay, let's see, something happened. Let's look at nighttime lights imagery. We brought nighttime lights. We compared, for example, when I compared 2 nighttime lights images over an area, I saw, okay, relative comparison of relative images. We saw a reduction in nighttime lights. If a disaster strikes, earthquake, floods, usually lights go off. So that's a very quick and dirty way to find out where things are. But that's just the beginning, okay? So you can see here that this is the result of that algorithm put in place over a map. And indeed, you know, you could see that, you know, the pixel even go into the sea. It doesn't matter because the images is, you know, the lights have been reduced so much, they've been flooding also the sea around. But the reduction is there. So you already know, like, if you were in charge of doing and supporting these people, you would say, okay, now we know where this is, but this is just, like we'll see now, this is just the beginning. In essence, whenever a crisis happens, we always have to do this assessment. This is what my colleagues, they came to us and say, help us do automatic assessment. Now, what is an assessment really? It's just answering questions. They really want to know in 1 hour, who is the affected, where did it happen? Because GIS is very good at answering where things happen. When, usually we know from the context, we know the floods happened 2 weeks ago, earthquake happened this morning. And also from there now, you can sometimes also deduce how much debris, how many buildings, what percentage of the built up area was destroyed. This is what assessment is all about. And there's a certain kind of linear flow there. When something happens, either it's natural, anthropic. Think about bombarding, think about all the terrible wars that people seem to be, you know, nations seem to be carrying today, as opposed to several years ago. These are all disasters, and we always have the same type of idea. The final goal is a mitigation, recovery, and help, you know, helping this area. So the UNDP and many organizations are in need of this type of tool, like Maria already said, and we are already there hiring people, and not only these organizations, governments, companies, and GIS are very useful because they can answer this type of question. So, you know, you ask yourself, what does it really mean to assess, actually? Because it sounds like very fancy English word. But let's see. You know, what you see here is satellite image with some boundaries. So once you identify the location, which we could do either by nighttime lights or by just knowing from the context, from news, we already start with, you know, with an area. Okay, this is what we are interested in. And usually we want to derive some kind of information. Assessment is about evaluation and getting a sense of what is on the ground. And whenever we do this assessment, we have to report it. Usually we report it at admin levels of various types, of various forms. Why don't necessarily they don't have to be admin levels. Sometimes they can be free polygons or areas or whatever, but it's always an area of interest. That's very important. So we have an area of interest. That is also at the same time, you know, there are also administrative units. What you see here, for example, is a population distribution from WorldPop 100 pixels, 100 square meter pixels with population male-child density. So just by overlaying, you can get a sense. Okay, this is where the kids are. The female kids are here. But of course, you need to count them, you need to sum them up. Why is this important? These are vulnerable categories. Whenever a crisis happens, you want to go and help the most vulnerable. So knowing where they are, knowing how many they are, really helps you drive your budget, helps you make requests, helps you set up the correct context of helping and reacting properly and correctly in the crisis. Of course, you need also to know where the roads are, for example. How do I get to, how do I help these kids? Well, we'll take trucks, we'll take, food, we'll bring them. So you need to know the density of the roads, various type of other information. So usually it's a complex thing, but the assessment really it's getting down to this. If identifying an area, having geospatial data distributed in space and time sometimes as well, time is important as well. And then just producing statistics and assessments. And in the end, it's a simple choropleth map which shows a distribution, number of kids, and of course there is a correlation with population. Of course the polygons have different area, but in essence, these numbers, this is an example of raw numbers that are really used down. And okay, there seems to be an area in the north, there's not a lot of kids there, so we don't really go there anymore. This is just, I'm just showcasing this as a very simple and basic example of, in essence, you can see that this is how the assessment look like. The map has the attributes, you can see the numbers there, you can put them in charts, in graphs. Obviously, on top of that, this is something very interesting. The green lines here show us, this is a simulation, it's not real, I just generated it, but I wanted to show you that, imagine that there's a flood in that area. If there is a flood, you always need to know where that extent happened, so you can compute and evaluate and assess the theoretical areas, the boundaries versus the affected areas. So what you need then, basically, the problem in GIS is not only about doing statistics, but filtering the pixels and roads and everything, clipping them and creating a second version so you can compare the theory versus the practice, the affected versus the total amount of people. So yeah, as you can see, what I described here is, in one way, there's a duality to this. There's this very nice way of talking about crisis, about how we react to problems, but at the same time, these are GIS operations. There's nothing fancy about it. I just did, clipping, cutting, zonal statistic, aligning, reprojection. So, the power is in the simple tools and chaining them together. When you do that, you actually resolve the problems, you respond, and you provide them the questions. So, for example, when we take this assessment further, usually, like I said, we start with polygons, right? And when you think about, okay, let's create a tool that helps us do this assessment. So how would you start about it? Well, we start with something which can get us admin areas, disregarding where we are on the world. So, well, you want polygons, and what kind of databases you have? Well, you have OSM, which has 9 levels of admin layers. You have OCHA, which has some limited country. You have ESRI servers. Okay, so basically that's where your administrative layers have to come, and they have to come quick. You have 5 minutes to get this data, not more. Obviously, you want to compute some special IDs. So to every polygon, you give it a unique ID, and you have H3 spatial encoding system, which guarantees more or less that if you use the centroid with a certain high precision, you always get a unique value for that polygon, because names are not common. So for example, if you go to Kenya and its neighbor from the left, I don't remember now the name, but my colleague Joseph here knows, they have both the same province with the same name. So if you use names, you get tricked. You cannot use it to join other data. You have to generate unique IDs to everything you do in this analysis. Of course, it's also smart, think about it, if you get this data from OSM. You get millions of vertices in Chile. Do you really need them? They're going to destroy your zonal statistic. No, you need to do simplification, because your goal here is to report on the administrative or different type of level. You don't care about geometry. What you care is the representation and the concept behind, so it has to be consistent and have a solid appearance. So this is the area of interest and the input data to this assessment. Next, there's components and variables. So what are these exactly? Now we have population, right? Population comes disaggregated. There's like 15 variables inside population. Groups, children, male, female, and sex. This is how you disaggregate it. You have roads, infrastructure, with electricity grid, industrial activities and sites. You have buildings. Buildings are like, there's a huge data set of buildings. It has over 100 million buildings. So we'll see how tricky it is to handle those. My colleagues in crisis, they cannot even actually download this data. If you open like a country like Bangladesh that has a lot of people on a small area, you start downloading buildings, you're done. I mean, you just cannot do it almost. You have to download all the files, then you start working with 15 gigabyte files. Not everybody has a powerful 100 gigabyte machine. On top of that, cloud machines are weak. The cloud is designed to split the data and work on 16 small units. That's how they make money. They sell the same computer 3 times. That's why they are rich. So I know that because I'm following their core and virtual machines. But this is why you have to, we have to be smart about all this work that we do. We don't have a lot of power. Then we have land use, livestock, for example, is important, and also socioeconomic indicators. You want to go and help people who are the most poor, who are deprived of various things, who don't have a good status, socioeconomical, let's say. So these are the components. Then you already started, you see the 2 pillars are here. We have the polygon, an area of interest, where we will evaluate the things and do the assessment and the variables that are going to be evaluated to build a kind of complete picture of the assessment. So what does this assessment really, now finally we're getting to it. It is usually really smart downloading. That means you need to have, for example, if you have like every variable should be at least coming from 2 different sources, and we should be able to harmonize it, and if one source is down, we need to go to the other. We cannot produce a software which says, oh, sorry, but Google decided to take off this server today, so we don't have any more of the assessment. This is not the good way to do it. Then we need to follow, for example, we have standards like STAC, where satellite imagery is already served in a very nice way. So this is the first step, is to already download, and we have to think really like we have to be fast. Timeliness is of essence here. We'll see immediately what that means. Then we need to integrate it. So, for example, Rapida, the tool we designed here, chooses an equal area projection. Now, many people were looking at me saying, you are going wild a little bit. No, I'm not. I know that most of the time things don't matter so much. But if it gets down into small area, think about SIDS. When we say SIDS, these are small islands and development states. These are countries who have 1 kilometer width. If you don't have equal area projection, you can get really nasty results in those kind of areas. And the same is valid for extreme areas, Canada, Russia. If you start producing these, they expand multiple zones, UTM, Gauss-Kruger zones, let's say, they expand latitude. So pixel size at the bottom, in the Himalaya, is not the same in latitude, longitude as on top. So you already get, if you're not careful, get distortions. We fix it to 100 meters. And we use all sorts of tricks, like GeoHub Warp, and all GeoHub tools have a tap option. We align it nicely. So this is important when we do this integration. No data is a big issue. It's very data set specific. This is about the second step, integration. And finally, we do the zonal statistic. And it can be done using specific tools. And I love to use Exact Extract. It's incredibly solid and fast. It builds on GeoHub, or you can use GeoPandas, for example. Think about that you have already like polygons with with population male, female, active. You can compute dependency as a formula, and just with 1 line of code compute another variable which helps you do something. But the result of all these together, of the polygon, of the component of data, of all this process, is actually a very simple map. It's not very interesting. It's just a chlorophyll map, but the power lies in the fact that you're able to produce it in a couple of minutes, and then this can get used as a cartogram. Somebody who's not very spatially oriented, not everybody sees 3D curves when they look at the topo map. You show them these, and everybody understands. Okay, kids in the blue high polygons, that's where we go. You don't have to explain it 7 times. This picture is worth 1,000 words. You show it, everybody understands. You produce reports, you create documents, and they go share. You share them with governments, with superiors, with other colleagues. Everybody's on the same page. So in essence, this Rapida tool that we have here, we develop it. It's a very simple thing, but its power comes from the simplicity. It has to be solid. It has to work fast, and it has to provide. Actually, it has to deliver. So in essence, when we designed, because we are big geeks, we thought, okay, we have a lot of repetition here. Whenever you see repetition in software, you always design classes because code is going to repeat. So you create a super class that implements basic things, and then you just, for example, inherit it. So we have a component. Think about the component. Population infrastructure is a component with its own variables. And I just showed you the definition of these classes, but you notice there is this call method. This is a Python magic method, which actually allows you to call classes as functions. So the code gets really simplified. We'll see immediately what it means. But you can see already the pattern is there. You always download, you always evaluate and compute things, you resolve. We'll see all what it means in a minute. So this is not necessarily important. I just wanted to show you, like, these are just two classes in the whole software, and simple is better than complex. Never forget that. So remember, I told you, like, this is the main assessment function. This is exactly this code is a copy from the main assessment function, and you can see it does a couple of tricks. But at the bottom of it, it imports dynamically these classes. It finds the component, scans the namespace. There is a class equals import class, and then I create an instance. It doesn't matter what component it is. It can be population. This is generic coding using classes, and then the last line really does call like a function. I want to call the component. I pass some progress, so it tells me what it does. These are the variables, so you can say GDP mean, for example, population, female, male, and then I don't know, number of buildings. Sometimes you pass target year, like with population, and you may want to do some other optimization, debugging, and stuff like that. But what you see here is, once you design these classes properly, this is what you need. You just need 15 lines of code, and it works universally for everything, basically. Now, you have to remember that these people, these colleagues of ours in Crisis Bureau, they are no geospatial people. They are laymen from our point of view, from your point of view. You know about GIS, they don't know anything. They are economists because they do modeling. They are lawyers. They are administrative people. So to them, basically, we created this. To them, we have to derive something very simple. So we designed like a command line tool with packages, with subcommands. The admin command is in charge of getting you this data. Admin, this is where you start. And then we said, okay, so you don't get confused. We create a project as a folder. And a folder is a project, and a project is a folder. Everybody knows a folder. Nobody knows a project. But if you make this duality, it becomes simple. Of course, our project has some extra metadata, which helps them in case they get lost. But then the project command can create project, which takes care of projection, importing, masking, polygons. And it can delete itself. The data and analysis live in the cloud. So currently the tool is linked to our cloud. But that will be maybe made a little bit better in future. So we and also projects can be created, listed, deleted, published directly to GeoHub, to the main core platform, or uploaded to the cloud and shared with other colleagues. For example, if one colleague works and doesn't have time to finish it because it's night, the other one that lives in the other part of the work because it's morning and we work from home can start and just copy the project and continue with assessment. There is authentication, and this was very tricky but we found a solution to authenticate using multi-factor. That's very annoying to do that. I had to do some really ugly tricks. Multi-factor means that whenever you log in, you get an email and ping pong on the telephone. So this tool is doing some magic to do that for you, and it tells you, hey, this is your number, put it in the mobile phone, and then you get authenticated. So my colleague then can publish and upload the data, and then the assessment. So these are the building blocks. To an economist, I'm telling him, hey, I'm giving you tools to do admin to download administrative areas and generate them with the custom ID so you can merge data in future. I'm allowing you to delete and operate with this project. You also need to authenticate because we are in a corporate environment. And then you do your assessment and you don't care about anything. You know, I remember that I told you there are two, like, there is one generic config, which this is how we store these variables. So while we store, because it's possible that some of my colleagues, if they become really good and smart, you know, in terms smart with the tool, of course, they can go and create their own variables. You can see, just look at the child total. Child total doesn't have sources. It has a source. It can be downloaded directly, but it has, I can force computation. And what does it do? It actually contains male child and female children. So all children are just two other variables. So they can resolve each other. They are hierarchical. Population is the most complex here. And so there's all of them live in a file, and you always can, everybody can go and check them. And there is this rapid JSON which says, okay, look at the create command. That's very important. Who created and how did it? I created this command at what date over what countries. That's all information that they need. Again, now you can see already here a print screen of the tool with all subcommands and an example of how it looks in the, you know, we store everything in a folder in VRTs to avoid space and TIFFs. Sometimes because depending, you know, TIFF is universal and very powerful if it's made as a cloud optimized GeoTIFF, and a geo package. There are other solutions. I would have maybe preferred to use flat GeoBuffer in a folder instead of geo package, but you know, there's pros and cons, so let's not spend time here. But you can see how it looks like. There is this tool now that operates and does all the work these crisis guys need. So this is I just put it as a background, and you know what it is here? This is what happens when I run, for example, at the top line, I'm telling it, go over population and fetch me and compute the female child. Just watch what happens. It goes, it fetches data, authenticates, refreshing the token from Microsoft. Then it goes to Azure, fetches data. Then it reprojects. Then it moves and says, okay, I'm trying now zonal statistics. You always see indicators browser. I put it in debug mode specifically so you see how many requests and what it does, just to compute one thing. To them, this is like they don't see anything of this. They just see some browser and then progress nicely moving and tell them, well, we are done. But to you, you are the one who have to see and look what happens here. You have to code this. You know, you as a future geospatial people will have to design software that will do what we see here, but will show it completely from our users. So now we can move a little bit and talk about some of these components and variables. So for example, population is very simple. Everybody understands it. You know, it's a country based. We took it from WorldPop, right? And we converted it automatically and hosted it in a spatial temporal asset catalog. Okay, but then we also did aggregation. So for example, in WorldPop, the population is aggregated in groups like below 1 even. You have infants, right? If you do vaccines, that's important because you need these small kids. You see, where you have the highest number of kids. It's very important to have this kind of information. And then basically, we also implemented a very simple forecasting. That's why we have a year just for population using a dynamic growth rate population generic model. And then you can ask it in future. Theoretically, this tool can give you population in 2028. It's you know, it's a question how well is that forecast. But because we're not in the business of forecasting people. But again, remember, something is better than nothing to them. They really need to know, you know, what is the trend. So this tool can even tell them what is the trend and do the assessment. So this is, for example, the population. So there in the first source, you can see that this population is actually constrained. Very important. The WorldPop data that is constrained has been generated with a model, with a geospatial model that is forcing population to appear in pixels that have buildings. So it's not distributed equally in space. It's anisotropic, basically, very much anisotropic, because population density is not something that is homogeneous. You have cities with huge density, think about Cairo, and then think about Sahara, completely, like a very good example. That's why we need to use constraint. So that's why we get correct statistics when we do evaluation over administrative units. And also UN adjusted, well, this is something that is our thing there. You don't want to differ your statistic too much from the official UN. They will differ anyway because of God knows why, rounding, anything will do. But you don't want to have, if we can, we want to be as close as possible to UN. Now, I'm going to, from all these other components, I think the buildings are one of the most interesting. And I really I created some slides to show you how differently you need to think and act if you are to provide operational service level of work. So the source of the building is simple. There is a Google, Microsoft, and OSM data set provided by a Belgian company, Vida. So we just took it. It's huge. It's divided by country in a very new format called Parquet and flat GeoBuffer. Now, flat GeoBuffer is a very important thing here. Why? Because it's one format that can have only one layer inside, but it has spatial index very nicely done. So you can really make spatial queries, and it's going to be faster than most of the other formats. It's binary. It can be consumed also in the browser directly already. So this is a very good thing, like, to have this type of data. Now, when we want to download the data, for example, let me give you one clear real-life example. My colleagues, before they asked me about it, I said, okay, here's the data set. They went to India and they started downloading. You know, the India data set has like 57 gigabytes of buildings. And I don't think they were all when they stopped. After 2 days, they said, we can't do anything. So how did we approach it? Like, it's completely different. GDAL, which is the project which I love a lot, has introduced something called Arrow API. This is a format of data that is cloud friendly. Okay, I'm not going to go into details, but this format, as opposed to, like, you all know when you want to do something in geospatial with coding, with Python GDAL, you iterate over features. Now, this Arrow API has this property of working on batches. So you can tell it, the maximum batch size is 65,000. So you can operate in units of 65,000 buildings, and they work super fast. So this is exactly why this is super. Without this Arrow API, we couldn't download these buildings anymore. So what we did, I designed a function to work in parallel. So for example, if I have a country and 5 polygons, each polygon takes the bounding box, takes the data source, and operates in parallel, and then write to the same data set using this. Read using Arrow API and write in batches. So suddenly, from 6, 7, 9, 15 hours, I was able to download, let's say, Bangladesh buildings, half of the country, in 30 minutes. And they can wait 30 minutes. They cannot wait 7 hours. So without these new technologies, and you see the very different approach, obviously, once we have this, then we do the assessment. And even here it is going to be, I specifically extracted the building because it was one of the most difficult, but my colleague has hit even harder work now with the land use, and we'll see. So you remember that the problem that with buildings, what is the problem that we encounter with buildings, for example? And you will see how nicely the theory and the practice is. Imagine in this area, there's like 11 million buildings in reality. Okay, now those buildings, basically, if this is a flooded area, you have to actually evaluate the buildings inside polygons, but also the buildings in the flooded area. So you have to do point-in polygon. Look how many vertices you have. Multiply those vertices with millions of buildings, and you are in trouble. You either need $5,000 in 24 hours to scale these on 100 machines, or you need a little bit of energy and some snack and work and do a better job. So when we say masking building, what does it mean? You have satellite image in the right side with clear buildings and the flooded area. So we're just selecting those buildings basically there, right? When we do the masking, this is the area where we start. Okay, we have some. Now we have the mask. We have also polygons. We want to compute number of buildings inside the mask in the district, but number of buildings, total number of buildings, to compute percentage, for example, that have been flooded, right? So, okay, this is my district. You can see those red dots. Those are all buildings there. There's a lot of buildings. It's just in this one district. Okay. And the problem of selecting a building is you can see the mask with the blue, left and right, flooded, not flooded. So, I just created this nice graphs with you using QGIS. So you can all see, because when I work, I don't really necessarily all the time need visualization, but it's good to see when we speak about it, what really happens here. So what I did, instead of like my colleague just tried to use, okay, select all buildings that intersect this other mask. After 6 hours, we just give it up. So then it forces us to think. So what did we do? We took centroids of the buildings, and each centroid with the code, these 4 lines of code that you see on top, we computed the raster index, for example, in the mask. We created the mask as a raster of 100 meters, and every centroid we computed using a feed transformation, the corresponding index, the pixel coordinates in the mask, and then we look in the mask, is it 0 or 1? Now these actually reduced the time to a couple of maybe 20 minutes or something, parallelization and all this. So sometimes really this is the mindset that you have to have when you work for this crisis. If you just run a SQL and wait, as I said, you either paid up $5,000 for the operation to Microsoft, or you can think about it. You will say, okay, I don't really need to be perfect. I can take the centroid of a building. I can compute the index where it falls. I can look in the mask if it's true or false, and I know, more or less. Of course, there's going to be errors, but 99.9% are going to be well computed. And this takes a couple of minutes. It's much, much faster than comparing millions of vertices against millions of vertices. So you have to really and then of course this is also parallelized. So all the code is in that repo, with kind of sometimes this parallelization and multi-threading is not something that we are really prepared to do in school, because I had to actually learn it in my professional life. And you know what forces you to learn it? Life. You will just realize that what you want to do cannot be done. It's naive. So you have to start tricking the system. And you trick it by saying, oh, I have 16 cores on my machine, let me use them. Otherwise you can't do this. So for example, when we want to mask buildings, this is what really happens. I pre-allocate the data set. I read the polygon, I prepare a dictionary with polygon ID, each bounding box. Then I start four CPUs. I said, okay, these CPUs are going to be used for this operation. Each CPU takes the polygon, a bounding box, and a source of data. Then it's subsetting, it's reading the data, the buildings inside the bounding box. That is very fast. Then it's computing the centroids, it's computing back the indices, it's masking, and then they communicate back to the main thread the results, and the main thread is picking up the results and writing them to the disk, forcing it as you write. As this works, the data is written literally to the disk, because if something goes bad, at least you save as much data as you can. So normally this operation would be in ArcGIS model builder. You would have 3 boxes and the result. It would appear incredibly simple. In reality, once you start computing these large areas, then you need to behave. You need to produce something like this. This is actually what really gets the job done. So think about it like a flood in India, that without this kind of approach in Kenya and any areas where you have a lot of buildings, you wouldn't be able to compute anything. The last component that we have here is the land use and cover, and this has been very interesting. So, this is a very basic thing, land use, right? You would think yourself, if I ask you, give me a land use map, and you would give it to me in 5 minutes. Just go to somewhere, ESRI, ESA, they have a global layer, and that's it. But then I tell you, give me a land use map from March 2024. Okay, that doesn't sound so simple anymore. We want only 1 month. Okay, we use Sentinel data. Is it cloudy? Is it not cloudy? What do? We classify it. So we found a model actually from Google, which was trained on Sentinel-2 L1C. Very important, because L2 is not available globally. It's only mainly in Europe and developed world where they have calibration to L2 level, processing level. But L1C is available everywhere. So they trained the model on L1 to be globally, and then basically we could actually fetch data from start for a certain time of period and create a mosaic of L1C, raw uncalibrated data, give it to the model and said, okay, give us the land use classes. And it works extraordinarily well, to be honest with you. I was always a skeptic about AI, but I can tell you that if I see progress and it's happening, but anyway, the process right now, we are actually working on it. It's very complicated. Normally, like if you think about this, is a process. This is a job for a week. We need to do it in half an hour or 1 hour. So that's actually how the level of precision and speed that we have to get in there. But the result is fantastic. Look at this prediction. You can see it feels very nicely with the water, urban areas with buildings, cover, like I don't have a legend here, but I just want to say this is the output of that model on Sentinel-2 uncalibrated 2-byte data. So it's very interesting. So why did we want to keep them in a crisis? If you go, if they come to me and say, give me land use, okay, what was covered with water? What was urban before? If it's an earthquake, you need this kind of map. But if your land use was created by aggregating data over a large area over a period of 1 year, you're really not sure what you're getting there. I mean, it's representative on 1 year, but is it on 1 month? Absolutely not. So this is why we choose to do it in this custom way. This is the last component, and I tend to believe it might be even more nasty than buildings. But with this one, we close basically the tool. So we have a couple of lessons learned here, like, don't keep your data in memory. If you read the data set, with 3 polygons, it's so nice. Everybody is master. But if I give you 50 million polygons, well, life is going to give you a bit of trouble. So partial reads are your friends, looping, you always have to divide things and use smart formats like COG, flat GeoBuffer, PM tiles. These are all data formats that seem very weird, but they help you at this work. Of course, I/O, managing I/O, like asynchronous for public cloud. These guys are powerful. You can ask, like, when we download Sentinel, Gene, my colleague here, has implemented, has broken down one image into 4 chunks of bytes, and in parallel is downloading each part and assembling the image. From 1 minute, he got 50 to take 10 seconds. And that's how you have to operate. Multi-threading, asynchronous, sometimes are also for CPU. So whenever you use multiprocessing, if you're not careful, you're going to blow up your computer. Because the way Python works, if you use multiprocessing, the data that each process takes is copied. It's copying the data. You have one NumPy array, and you want to break it down into 5. Each process is going to get a big copy of the data. So if you think by parallelizing you're going to do the job, you're not. What you need to do is to convert numeric Python array to a C pointer and pass the C pointer to the function. That one is going to be passed by value. And then each process is going to reconstruct the big array and operate on a small data area individually. That's the only way you work with multiprocessing and NumPy arrays. GeoPandas is not as easy anymore, but NumPy arrays, which I personally love the most, and they are very close to raster data in Python and their native model, they can be operationalized like that, like using sharing memory, basically, and pointers. So pointers are important. Without them, we cannot do parallelization in reality. Okay, everything has to be broken down. So you either break things on polygons, then you risk, just think about it, you have admin 2 levels, but some admin 2 units are countries, while others are very small villages. So in that sense, you may be just going to a Gauss-Kruger, creating 100 by 100 kilometer squares and operate on that level. So you have to always adjust. And always for your users, you have to tell them, okay, this is what's happening, this is what we do and not. So on top of this, I want to say that all this library is command line, but we developed now, my colleague Joseph has developed notebooks. So the crisis bureau colleagues go to a Jupyter server and they have notebooks. So if they want to run one, we are doing also wonders there. Like we created a GUI to display, and everything is already GUI based. So we are creating a system. But in essence, these guys who are economists, lawyers, administrators, I don't know what are they, but they are not good with JS, and yet they have to produce assessments in 15, half an hour, 1 hour. In 2 hours after this happened, they have to have the assessment. then it goes into processing, and next day there is a web document, web accessible story map that goes to governments and people who have money. So it's and decision and power. So it has to be looking good, it has to be credible, and it has to be fast. I think I'll stop here because I reached the end. If you have any questions, but it was a real pleasure. I hope I didn't bore you with all this.
Thank you, Ioan. I want to ask you if you wanted to show the GeoHub very quickly in such a way that then the students can also try to use it, having an idea about, because now they know what there is behind it, and so probably, and I see that there is Ralph Douglas also here. And they can see how it is working and what they can do. Also because GeoHub is an open platform. And so if they want, they can try also to use it. And they can see what there is, which are the examples. If you want to quickly present it.
Well, okay, I'm going to be very short. So it's important, like it's a web platform. What I want to say, and it's important, the next step of this Rapida project that we did for the crisis guys is to move all that functionality, all the data into this web environment. Now we want to do that. First we needed to develop it, and we needed to make sure we capture the requirements they have for us. And second, now we're going to start moving into the server. But in essence, it's just a simple like backend using zonal statistic and maybe manipulation of geodata frames in pandas. So now let's get back to this. Right now, like it has a GeoHub, like you remember the first slide that we had there. Let me go here. Right, you see the data. So it has a data section. This data is in the cloud. We're just pulling it. And if I look at some data set, okay, this is a data set, it's lives in the cloud. I can preview it, I can visualize in multiple ways. There are permissions. I don't know if this person created this data set, no idea what it is, but it follows some standards. So this is the data part. This really goes to the aspect of the centralized accessible data store. The data mapping services are like, okay, this is a service that we have. This powers the vector tiles. There is another one that is e-tiler, and this powers mapping. It takes cogs and create pictures. So this is the second component here, the data mapping services, this open source software. So D-tiler is basically a server, a cloud optimized server built on top of raster.io and GDAL and all these fantastic libraries, using cloud optimized GeoTIFF as a format. So this is the second component here. The last one is we also have a library. So when we developed GeoHub, we married a couple of technologies together, and we created now a library of components. Okay, so these are some of these components. So we took this standard that UNDP uses, and we created various type of components that we, this is a sidebar, obviously, but we also have like geospatial components. So you can see a heat map component, for example, that creates a heat map, and this is a library. So theoretically, if you're proficient with with web coding with JavaScript, then you can start using it. Obviously it requires a little bit of time. It's built with Svelte, which is an alternative to React, and this is the third bullet, and they together form this platform.